71. Yes, very good. Is this the problem we did in class last time?
No.
No. Even if it is, it's fine. So
Oh.
we're given f of g of h of x. So 1, 2, 3. Where h of 1 equals 2, g of 2 equals 3, h prime of 1 equals 4, g prime of 2 equals 5, f prime of 3 equals 6. And the question is asking us to find r prime of 1. Good pick. So what do I have to find or determine first before I plug in 1?
The overall structure.
I have to find r prime of x. If I don't have the derivative, I don't know. I don't have anywhere to plug in 1. So this is the first function, this is the second function, and this is the third function. So this time we have an innermost, which is h of x. The next level up is g, and the outer function is f. So h, f, g, and f. However, when we differentiate, we start from the outer. So r prime will be prime of g of h of x times g prime of h of x times h prime of x. They're all multiplied. The chain rule requires everything to be, all these are factors, 1, 2, 3. So now I can find r prime of 1, first of all replacing x with 1 everywhere. So f prime of g of h of 1 times g prime of h of 1 times h prime of 1. And now let's see and plug in what we have. Do we have h of 1?
Yes.
H of 1 is 2. Do we have h prime of 1? 4. So for now, this is what I'm going to write. 4 goes in front. F prime of g of 2 times g prime of 2. Is this okay so far? So now I'm asking myself, do I have g of 2? Yes. So that is 3. Do I have g prime of 2? That is 5. So therefore I have now 5 times 4 go in front, 20. And I have f prime of 3. Now do I have f prime of 3? Yes. So this will be 20 times 6, which is 1. Of course, it's 120. I looked at 3 here. I'm not... no, keep an eye on me and what I do. Because sometimes 20 times 6 is 180. No, it's not. No, it's not. In my head, I was multiplying by 3. Very good. Is this clear? All steps? The answer is 120. Other questions? Anything else? Anything else? Anyone? Okay, so in that case, I'm pressing forward and we finish the chain rule and implicit differentiation. However, I do have a little bit of leftover from the chain rule and a little bit of leftover from implicit differentiation. Okay, so let's go back for a moment. We know that when we differentiate e to the x, this is the only function whose derivative is, which is 1. Correct. Or what if I have e raised to a function, prime? So this is to the f times f prime. Very good. Perfect. Now, here's my next question. what if I have any other number but e? So I'm going to say a. A is not e to the x power, and I want to differentiate this. So that's my question now. Okay, I'd like to go back to a property of logs that we don't really emphasize in pre-calculus, but we have to discuss it now. And here's the property. Do you remember a raised to log base a of x? What does this equal to? This is a property, one of the many properties of logs, logarithmic functions. Indeed, absolutely. Okay, so then, if this is clear, yes, no, is this okay? As long as this base and this base are the same. So let me give you an example. Let's say 5 raised to log base 5 of 20. This is 20. As long as this base and this base are the same. 5 raised to log base 4 of 5 is not 5 because these two are not the same. Now, if we want to prove this, we can. We have to change the exponential equation into a log equation, and then we'll realize that this is true. Do we need to do that, or do you remember the rule? Remember the rule? Yes? Anyone needs me to prove this? Oh, so let me know if you do. Okay, so then I am going to use this property and create something for a to the x, and you'll tell me whether you agree with it or not. I'm going to say that a to the x is identical with e raised to natural log of a to the x. Let's see if this is acceptable. Forget about this side for a moment. What will this equal to? E raised to natural log, which is base, the same base, of a to the x. What will this equal to? Right, by this property. Do we see it? One more time. So the base is e. Natural log, now it's a different notation because it's base e. For natural log, we use ln. So this is this natural log with base e. And this quantity is the x. Agreed? Okay, perfect. Now, I need one more property and then we proceed. Is it clear that log base a of x to the b power, the b comes in front as a factor? This is the power rule. Do we remember this? Okay. So if we remember this property, then you will allow me to put this x right here and the exponent in front of natural log. So for now, I will say this. Correct? Okay. What are we after is this. So I'm going to differentiate both sides. The left-hand side is what I'm interested in. So it's a to the x prime. But now, how do I differentiate the right-hand side? Well, going back to e raised to a function prime is e to the function times the function prime. Very good. So then, e to the function prime is e to x natural log a multiplied by the inner function prime. But this is a constant. This is like saying 15x. Natural log a is a number. So when I differentiate this, what do I get? 1 times this. So how do I differentiate 5x? What do I get? Good. In the same way I differentiate, but we don't write anything behind a square root. We don't write anything behind a natural log. But let me write it in a different way. So natural log a times x prime will be natural log a, because x prime is 1. So times natural log a. So for now, this is the intermediate step, but we know exactly what this means. Right? E to x natural log a is a to the x. I'm going to replace it. So whenever we differentiate an exponential function with a base of any number but e, what do we get again? Let's see what happens if a is e. What will happen? What will happen if now I have a special case in which this is e? What do I get on this side?
E to the x times natural log of e.
Exactly. Exactly. So this is the general case. Exactly. So then this was what was I did not get the chance to show you from the chain rule. And now, of course, I'm going to ask you this. When we differentiate an exponential function or an exponential expression with a base other than e and some function, what does this equal to?
A raised to the derivative of the function.
We cannot do that. It's the chain rule. All we have to do is consider that this is a function.
So function with a function. Do derivative.
Okay, so we forgot. That's okay. That's okay. Let's go back here. What did we say about e to raised to a function prime? So e to the f times. Good. So now let's do the same thing for a raised to a function.
Natural log of a.
That's it. It's exactly the same thing. It's just that x now is a function. I have to multiply by f prime. Any questions? Okay, and the little leftover from 3.5 deals with inverse trig functions. How many trig functions we have? Good. How many inverse trig functions we have? 6. Very good. I'm only interested in 3 of them. If there is anything, I didn't mean the -1, of course. If there is anything else beyond those 3, the formulas will be given to you. You don't have to memorize them. Oh, of course. I'm sorry. These 3. Don't trust me today. I made an announcement. Don't trust me today. Okay. So this is another way of saying arc sine. And this is another way of saying arc cosine. This is another way of saying arc tangent. It does not mean 1 over tangent. It does not mean 1 over cosine. It does not mean 1 over sine. It's just the inverse function of sine, the inverse function of cosine, and the inverse function of tangent. These are the only 3 that I ask you kindly to remember. Commit to memory. So sine inverse prime is 1 over the square root of 1 minus x squared. The second one, cosine inverse prime, is exactly the same but with minus in front. And of course, our longtime friend, tangent inverse. If you remember, we graphed it several times. We determined limits. So this is major. A very important function is this. So these three have to be committed to memory. Sorry about that. Now let's practice this, and I'll let you choose on page 216, problems 49 through 60. Page 216. Anything that you would like to pick, or I will, for you, that has any problem or problems that have these three functions: sine inverse, cosine inverse, and tangent inverse. We want to choose, or will you allow me to choose? Okay, so let's say 53. In 53, we have g of x equals the square root of 1 minus x squared multiplied by arc cosine x. Remember, arc cosine x is the same with cosine inverse, just a different notation. Honestly, I prefer this because when I write a test, I don't have to put the power. It's easier if I write arc cosine. Very good. So we want to find g prime of x. How do I determine g prime of x? I look at the function first and I say, I see this function is a of two functions. Here is function 1 and here's function 2. So I have to apply the product rule. If you like the order I presented the product rule in, fine. If not, use your own method. I'm fine. So when I differentiate this, we just reviewed it a minute ago. We didn't apply it, but it was in the previous lecture. How do I differentiate this?
Negative power.
Yeah. So let's go back because this is very important. That's okay. We're gonna write it again. So when we differentiate the square root of a function, we get 1 over 2 the square root times the function prime. It will save us a lot of time if we remember this rule. Because otherwise I have to put the power 1/2, and then I have to put the power in front, and then I have to bring it to the denominator, and then it's going to have negative, right, if I don't bring it to the denominator. So this is the best thing one of the most important items to remember. So the square root of f prime is 1 over 2 the square root of f times f prime. Very useful. So I can write it again here if you want. Would you like me to write it again? So here's where it's coming from. Let's refresh our memory. We do know that the square root of x prime is 1 over 2 the square root of x, correct? That's how we know that the square root of a function prime is 1 over 2 the square root of the function times the function prime. So these two go together. If you remember the first one, you should be able to remember the second one. It's just that it has times f prime. That's the only difference. Is that okay? Better? Okay. So now we'll go back and try to find g prime. So then the first function, the square root prime, will be 1 over 2 the square root of, very good. And then in parentheses, I have to have f prime. The derivative of 1 is 0. So the derivative of this function inside is negative 2x. Is that okay? Yes? Times the second function, arc cosine x, plus. I write plus because this is a sum of two. This is the product rule that changes into a sum. Okay, now I copy the first function, which is 1 minus x squared, and I have to multiply by the second function prime. So cosine, our cosine or cosine inverse prime is negative 1 over the square root of 1 minus x squared. So I'm going to put this in parentheses. Negative 1 over the square root of 1 minus x squared. So far, so good? Okay. I'm going to try to simplify a little bit, and here's what I'm going to do. I see a positive 2 here and a positive 2 here. Now you can say, well, let's get rid of this and we have minus 1. That's possible, but I'm looking at the first expression and it has the same square root in the denominator. And I prefer, instead of simplifying here, these two, and getting minus 1, I prefer keeping the fraction as is. So the numerator will be negative x arc cosine x. And here the numerator will be negative the square root of 1 minus x squared. Since we're not doing anything else with this function, it can stay like this. It can also be negative x arc cosine over the square root minus 1. That's fine too. But you will see in chapter 4, we prefer and we have to have simplified forms of rational functions like this one. It's a combination. It's not a pure rational. But you will see what happens in chapter 4, what we're trying to do with the first derivative. Okay, should we choose another? Yeah, let's look at 58. It looks interesting. So we have y equals cosine inverse of sine inverse of t. There are only two functions here, right? The outer and the inner. Since this is plain t. If instead of t we had 15t, then it would have been three functions. So y or dy over dx, whatever you prefer, in this case it doesn't matter. The outer function prime. We know that our cosine prime is negative in front, then 1 over the square root of 1 minus what?
Squared.
Sine inverse squared. Sine inverse t squared times. So let's do this together. Okay? So I have to differentiate cosine inverse of something, right? It's negative 1 over the square root of 1 minus that something squared. But it happens that this is sine inverse t, so that's what I have to write. So I differentiated this, but now I have to multiply by the inner function prime. What is the inner function prime? It's the positive 1 over the square root of 1 minus t squared. We don't have to do anything here. This is it. We can't do anything. Please do not multiply the negative 1 because it's not a power here. It's totally different. Do not multiply this and say it's 1 minus sine to negative 2t. This is just a notation of a function. This is arc sine squared. So don't get confused on that. Okay. Do you think we need more examples, or if not, we can move on to section 3.6. Finally, we talk about log functions. That's why I left that little explanation for today. So you think we need more examples with, yes? Okay, very good. Robbie, you want to choose, or you trust me to choose? Okay. That's an honor coming from you. Okay, so let's do a tangent this time. Yes. I'm going to read. What if I get your input? Okay. So there is a tangent here, tangent inverse squared. There is a tangent here, tangent inverse of x squared. And I also see here a tangent inverse of all this. 40, which one? 49, 50?
50.
50, perfect. Let's look at 50. 50, we have tangent inverse of x squared. So y equals tangent inverse of x squared, and this is 50. Page, again, 216. So we want to find y prime, or dy over dx, and we have to differentiate tangent inverse. So please don't get confused and put a negative in front and say that you subtract 1 from the power. If that confuses you, what I would do, I would recommend this. Change the whole function into arc tangent of x squared. So if that notation confuses you and you may be tempted to put -1 in front and subtract 1 from the power, that is just a notation. Tangent is not raised to the power -1. Is that clear what I'm saying? Okay, so you prefer this notation or this notation? It's fine with me. It doesn't matter, we're going to differentiate it anyway. But is it clear that these two are the same? Okay, so then if we want y prime, what will you say? Yes, times
Inner function squared, which is 2x.
Very good. Nope, that's it. Times the inner function prime.
I said the inner function squared.
Okay. So then y prime again, if you want to rewrite it as this. And we cannot simplify it in any way, shape, or form. Is that okay? So it was, so arc tangent x prime equals 1 over 1 plus x squared. If this is a function, then this is a function squared and times f prime. So since our function was x squared, when we put it in here, squared will get x to the 4th, and f prime will be 2x. Everyone with me? Okay, do we need another or we move on? Moving on? Everyone? Yes? Okay, so we can always come back and do more problems. 3.6, derivatives of log functions. Here's what we know from logs. Every time I teach pre-calculus, I always tell my students that the most important relationship or piece of information from logs and exponentials is this. Any log equation can be replaced by an exponential one. This is the most important item that comes out of pre-calculus. Every log equation can be presented as an exponential one, and vice versa. Double equivalency, we've seen this before in the precise definition of the limit, meaning this implies this, this implies this. So what is the exponential equation that replaces this? A raised to power equals, that's it. A raised to power y equals x. So any log equation can be replaced by an exponential one. What am I after now? Well, I'm trying to explain when I differentiate this, what do I get? So, like before, we know how to differentiate an exponential function, a polynomial, a product, a ratio, a function composition, but we don't know how to differentiate a log. This is what we are after right now. So, if I want to differentiate log and find out what it is, I have to differentiate this function by implicit differentiation, correct? So if I differentiate this side, I have to differentiate this side. I don't know how to handle this just yet, so I'm going to shift over right here and see what I can do. So we're going to start with this exponential equation. A to y equals x. And I am going to differentiate implicitly. So now please pay attention that a is a number. A is the base. Y is this function. What function? Log base a of x. And x is the simple variable x. But y is this function. So forget about this for a moment. We have this equation. We want to find dy over dx. A is a constant, x is the variable. We are after dy over dx. What do I have on the left-hand side? Go back to 10 minutes ago. And we said, that's why I needed this now. Here's what we did. A function, prime. It's the base, a raised to the function, times f prime, times natural log a. We remember this from a few minutes ago. Okay, let's do that. So let's dictate one more time, the left-hand side.
So A to times y.
Yes.
Okay,
Times a equals. Perfect. From this equation, what do you think I'm going to solve for?
2 ideas.
Of course, which is the derivative of the log function. So dy over dx is 1 over a raised to y times natural log a. Okay, so this is log base a of x prime, because dy over dx is this derivative, the derivative of this function. But remember a, y, so I have a raised to y. I have a, and y is log base a of x. Right? But what does this represent? We just had this property a few minutes ago. Yes, indeed. So coming back now to finish up my derivative, then this is nothing else but 1 over x natural log a. So now let's write the final. It's here, but let's summarize. Log base a of x prime is
1 over x.
and now I'm going to ask you how much is natural log x prime. So this was the general case, but now natural log is a special case when a is how much?
E.
Correct. So what will the answer be then?
1 over x.
That's it. 1 over x. But we have to remember both, because you may encounter another base than e. And when you do, don't forget about natural log a. I would like to practice these. On page 223. We can choose anything you want from 2 through 22 for now. 2 through 22, page 223.
Number 6.
Number 6, very good. Let's try number 6. Number 6, perfect. 6, 6. I see it. Very good. That's y equals 1 over natural log x. Perfect example. Okay, we are asked to find dy over dx or y prime. So my question is this. Since you know me a little bit, what do you think I'm going to do first? Rearrange or simplify or clean it up? I will do something to it. Yes.
Just the natural log of x to the -1.
Otherwise, I have to use the quotient rule. I don't want to mess with it. The top prime will be 0 and then minus and this and that. This is much easier, I think. So now dy over dx, and actually it's the only thing I can do, right, to that 1 over natural log. So dy over the dx is, I have to bring the power in front now, right, because I differentiate, -1 times natural log raised to which power?
-2.
Correct. Now times the inner function prime. 1 over x. And yes, now I can go back. I don't like negative exponents. And I can do this now. Be careful not to put the power on x. The power 2 in the denominator is on natural log. Any questions? Please stop me if you have questions. Anyone? Please? Anything? Any doubts about this? Please ask. We'll work on other problems in a minute, but any questions on this? Okay, so please let's select another. I would like to look at 11 if you'd like, and then definitely 13 because I need to show something, or 11 or 13 are very similar. You choose. Or I will. 11. Okay, very good. So 11, g of x equals natural log, and in parentheses x, the square root of x squared minus 1. Let me refresh your memory on another property of logs. Maybe we should look at both properties. If we have log in any base of a product, or if we have a log in any base of a ratio, how do we simplify these two? Nope. Exactly. Log A plus log B. So log applied to a product changes into a sum of logs. Good. Now, log applied to a ratio. Exactly, a difference of logs. Awesome. So please remember these two properties. Okay, so now let's go back to our function. We're asked to differentiate this. And you can say, just go ahead and differentiate it. Yes, I will. However, I would like to apply one of the properties that we see here. And there is one more, which we already discussed, that allow me to edit here. So log in any base of A raised to B is the same with B, log in that base of A. So these are the three properties. This is the power rule, the quotient rule, product rule. One more time from the top to the bottom. Product rule, quotient rule, power rule. Product, quotient, power. Okay, so if we want to apply the properties of logs on this function, what would you tell me to write? Very good. Natural log of x plus natural log of the square of x squared minus 1. Perfect. Now I have one more property. I cannot do anything to this. But to this, I can apply one more property. Which property is that? Obviously not the product, not the ratio.
Bring down 1/2.
Exactly. So this will be natural log x plus 1/2 natural log of the x squared minus 1. Differentiating this function will give us the same result as differentiating this function. This or this are identical. However, I prefer differentiating this versus this. Here's why. I have an outer function, but the inner function is a product. And it also has a square root in it. So we can definitely differentiate a function and get the derivative in both ways, if you would like that. But I would like to show you this one first. And then we can go back and do it again without applying the properties of logs. So let's do this. So g of x, g prime of x will be, so this is not a product rule at all. This is a chain rule once, but everything else is, I differentiate natural log first, and I get, very good, plus 1 over x, 1 over 2 stays, but then I have natural log prime, which is 1 over, oh, see, I did not write that for you. So what about log base a of a function prime? I should have. And then natural log of a function prime. Let's add these two in.
That'd be
1
over x times the natural log of a times.
Very good. And this one is even easier because it doesn't have natural log a. F times f prime. Because natural log e is 1. Should I do this again? Yes? Okay. So if you remember, we had a to the x. We had log base a of x. The derivative of this is 1 over x natural log a. But what happens if I have a function here? The only thing that changes is times f prime, nothing else. The same thing here. If I have a function, the only thing that changes is 1 over the function times the function prime. So that's what we wrote here. So natural log a of f prime is 1 over f natural log a times f prime. And the same thing for plain natural log. Natural log of a function prime is 1 over f times f prime. So now I think we're ready to finish this one up. So natural log prime is 1 over x plus 1/2 times, very good, times 2x. So these 2 will go away, 2 with 2. So I'm going to simplify it a little bit. So this is 1 over x plus x over x squared minus 1. Now, if you would like us to go back to the original function and differentiate it, we can. They will be identical at some point in time. That one requires more work, but we can show that they are identical. Do we want to do that or not? No. Okay. Do we need other examples with natural log? I think we should look at least at one more. Do I get to choose? Okay. Which one? Yeah, I said 11 and 13. They're similar. So we can do that. Or, yeah, let's do that. 13. G of y. The variable now is y. Natural log. Apply to a ratio. 2y plus 1 to the 5th power over the square root of y squared plus 1. Now, in here, I will not apply the properties of logs, only if you insist to do it without. It's not going to be an easy situation. So I recommend let's apply the properties of log and simplify this as much as possible. Instead of differentiating an outer function, which is log, and an inner function, which is a ratio, and one of it has, the denominator even has a square root. I would not ever attempt this without simplifying it using the properties of logs. So if we do that, what should I write?
The natural log is 2y plus 1 to the power minus natural log of the square root of y squared.
Good. One more step in which I don't no longer have products or quotients, but I do have a power. I do have a power in both.
5 natural log 2y plus 1 minus 1 half natural log y squared plus 2.
Perfect. That is perfect. And now we can differentiate g prime of y, or dg over dy, the derivative of g with respect to the variable y. Okay, so what do I write for the first one? I have the 5, and now I differentiate log. When I differentiate log, I have
1 over 2y
plus 1 multiplied by y is a simple variable, multiplied by
What's that time?
2. Good. Minus 1 half.
1 over y squared plus 1 times 2y.
That's it. I'm going to try to simplify it a little bit by just rearranging the whole thing, actually. And I simplify the 2's here. That's it. So 10 divided by 2y plus 1 and minus y divided by y squared plus 1. This is good enough because we are not taking this anywhere else. It would have not been as straightforward. Okay. Here's our next step, very important step. A function f raised to a function g prime. These are not variables. F is a function, g is a function. So let me give you an example on the side. Let's say sine x raised to cosine x. Question is, what do I do? And I'm not asking you to answer. It was just a rhetorical question because I'm going to give you the answer. There is no formula or differentiation rule, diff rule, for something like this. There is none. We can still differentiate, but first we have to denote it by y. So y is a function raised to another function. Since there is no rule, what do you think I'm going to do to both sides?
Take the derivative.
Apply.
Apply the log.
Exactly. That's why we talk about logs, right? So this is natural log y equals, I want to simplify the right-hand side. Very good. And now everything, the problem is solved. So if I want to differentiate the left-hand side, because I want to find y prime, I differentiate the left-hand side and differentiate the right-hand side. How is this called? Implicit differentiation. But actually, this process has, I would say, two names. One of them is logarithmic differentiation, combined with, in this case, with what? Implicit. Exactly. So first, we applied log. Fine. But we also had to use implicit differentiation. We didn't finish. You want to continue on the abstract case, or you want to work with functions? We can continue the abstract case, or we can go back to any combination, anything you can think of.
Continue abstract.
Okay, so let's continue with the abstract. We have a couple of steps to finish this, and then we'll work on problems. Okay, the left-hand side. So now I'm ready to differentiate. Only after I bring that function down, I'm ready to differentiate. Okay, the left-hand side, please. Now, we have to remember one thing. Forgive me for interrupting. We have to remember that this is a function. Okay? Good.
1 over y times dy.
Perfect. Indeed. 1 over y times dy over dx. Very good. Equals. Now remember, this is function 1 and this is function 2. I have to use the product rule now. I don't have g, right? So I will have to write g prime. That's it. That's okay. Times natural log f plus g times
1 over
f times f prime. Good. So how do I solve this equation for dy over dx? What will be my final step? I only want to get rid of this. How do I get rid of a fraction? By both sides by y. But since y is f to g, I'm going to say f raised to g. And I'm going to copy the rest. Do not distribute. That's all you need to do. G prime natural log f plus g over f times f prime. Well, I'm not going to ask you to do anything with the abstract case. So let's work on different problems to see how this works. We can start with the one that I made up, which is sine x raised to cosine x. And this is our y. What is my first step?
It's cosine in front.
But I have to apply log. Only log will do that, right? Natural log y equals cosine x times natural log sine x. Agreed? Only now I can start differentiating the left-hand side, differentiating the right-hand side. Let's talk about this and see if this is clear to everyone. Is it clear to everyone? Yes? Okay, let's do that. So, when I apply natural log to this side, I get this. When I apply natural log to this side, the power goes in front of the natural log. So then we have cosine times natural log sine x. Is that better, everyone? Okay, so now we're ready to differentiate. Our function is y. Y is what we're interested in finding dy over dx for. So, what do I have on the left-hand side? 1 over y times, very good, equals. Now this is a product, so it has to change into a sum of two different quantities.
So you'd have sine x.
Negative, this is negative sine x
Negative sine x.
times natural log of sine x, and then plus cosine x times the derivative of natural log of sine x.
1
Yes, 1 over
sine x
times the inner function prime,
times 1 cosine x.
cosine x. We're almost there. The only thing that we need to do to both sides to get with dy over dx is, that's it. Instead of writing y, I'm just going to copy the function sine x raised to cosine x. And this is negative in brackets. Negative sine x times natural log sine x plus, I'm going to write cosine cotangent. Cosine x, cotangent x. I changed this into cotangent. Why?
Cosine sine.
Because cosine over sine is cotangent and I was running out of room.
Would you take it, you edited it with 1 over sine x times cosine? Or do you want it?
Oh no, it's fine. It's the same thing. You can even say cosine squared over sine because you're multiplying them. But I try to avoid fractions if I can, but it doesn't matter. You can write cosine squared over sine or cotangent cosine, cosine cotangent. Okay, I think we need at least one more of implicit differentiation.